Hey everyone, today we're going to dive into the really fascinating world of artificial intelligence and ask a pretty fundamental question. How does it actually learn? Specifically, we're going to look at reinforcement learning, which is basically the powerful science of teaching a machine through nothing more than trial and error.
I mean, think about it. How does an AI go from knowing absolutely nothing to mastering a super complex game like chess or Go without a single person giving it instructions? It's an incredible question, and the answer really comes down to three core strategies that we're about to break down.
And to make this all crystal clear, we're going to use a simple analogy for this whole explainer. We're going to imagine teaching an AI agent how to solve a maze. Our little agent starts in a corner. It has no idea what the layout is, and its one and only goal is to find the prize at the end.
Okay, let's get into it. Before our agent can even begin to think about a strategy for solving this maze, it first has to understand the basic rules of the learning game itself.
You see, every single reinforcement learning agent, doesn't matter how complex, runs on this very basic loop. First, it looks at where it is right now. That's its state. Then, it takes an action, move up, down, left, or right. The environment, which is our maze, then gives it a reward. Maybe it's a tiny negative reward for every step just to encourage it to be fast, or a huge positive reward when it finds the prize. That action then puts it in a new state, and the whole cycle just starts all over again. This is it. This is how it learns, by just trying stuff and seeing what gets it closer to that big payoff.
All right, let's get to our first big strategy. We're going to call this one the judge. I want you to picture an agent that's trying to create a super detailed value map of the whole maze, basically judging how good every single square is.
So this is what we call a value-based method. The agent's goal here isn't just to wander around, it's to figure out exactly how good or valuable each square in the maze is. I mean, it makes sense, right? A square right next to the prize is obviously very valuable. A square that leads to a dead end? Pretty worthless. Once it learns the value of every state, the agent can just follow the path of breadcrumbs, moving from a lower value square to a higher value one, and that pretty much guarantees it'll find the best path.
Now, this judge strategy has a few different flavors. You've got Q-learning, which is kind of famous for creating the ultimate cheat sheet. It learns the absolute best value for every possible move you could make. Then there's SARSA, which is a little more down to earth. It learns values based on the actual path it's following right now, not some imaginary perfect one. And of course, when the maze gets ridiculously complex, you bring in the big guns like deep Q networks, or DQNs, which use these powerful neural networks to figure out the value of everything.
Okay, but what if an agent doesn't need to know the value of every single square? Well, that brings us right to our second strategy, the rulebook. This agent's goal isn't to judge anything, it's just to come up with a simple set of instructions to follow. This is the heart of what we call policy-based methods. The agent learns a policy, which, let's be honest, it's just a fancy word for a rulebook. So the policy might be something simple like, if you see a wall, always turn right, or at a four-way stop, just go straight. The agent starts with a totally random rulebook, and then through trial and error, it slowly tweaks those rules until it's got a set of instructions that solves the maze really well. It never actually has to know the value of a spot, just what the best move is.
A classic way to build this rulebook is with a technique called policy gradients, which you'll find in algorithms like reinforce. Think of it like this. The agent tries out a set of rules, and if that run gets it to the prize quickly, the algorithm basically gives that whole rulebook a big thumbs up. It reinforces the actions that led to a good result, nudging the probabilities so those successful rules are more likely to get used again. It's a really direct way of learning. Hey, what I just did worked, so I should probably do more of that.
And that brings us to our third and final strategy, the architect. Now, this is the most forward-thinking agent of the bunch. Instead of just reacting to what's in front of it, this one tries to build a mental blueprint of the entire maze first. In a model-based method, the agent's main goal is to understand the physics of the maze. It learns a model of its world. It figures out things like, okay, if I'm in this square and I decide to move right, I know I'll end up in that square and get a -1 reward. It's basically learning the entire map. Now the downside? Well, building a really accurate model of a complex, unpredictable world, that can be incredibly hard to do.
But here is the massive advantage. Once the agent has a good enough map in its head, it can plan. It can run entire simulations of the maze internally without ever taking a single step in the real world. It can try out thousands of different paths in its own imagination to find the absolute best one before it even moves. This makes it incredibly efficient with its experience.
So we have the judge, who values every single step, the rule book that just wants a simple set of instructions, and the architect, who wants to build a map. But you know, the real magic starts to happen when you combine these ideas.
And that's where actor-critic methods come in. Just like the name suggests, this is a team effort. This hybrid approach takes the rulebook idea from our policy-based methods and combines it with the judge idea from value-based methods, and together they create a much, much more efficient learner.
So here's how it works. You have two parts working together. The actor is the player. It's the policy, the rulebook that actually decides which move to make. And then you've got the critic, who's kind of like the coach. The critic watches what the actor just did and then says, hey, you know what? That was a better move than I expected. Or maybe, woof, that was a mistake. The actor then takes that feedback from the critic to update its rulebook. It's this fantastic feedback loop that helps the agent learn way, way faster.
All right, so let's just pull this all together for a quick recap. We've got our three core approaches. First, the value-based judge, who's all about learning the value of every single square. Then we have the policy-based rulebook, which just wants to learn what action to take from any position. And finally, the model-based architect, who learns a map of the whole maze so it can plan ahead. Each one has its own strengths, and together they really are the foundation of all modern reinforcement learning.
Now, this is all pretty cool, but you might be wondering, why does any of this matter? Well, it matters because these strategies for solving a simple maze are the exact same ones being used to solve some of the biggest challenges out there in the real world.
Seriously, you see these strategies everywhere. In robotics, where a robot arm learns the most efficient way to assemble a car. In game playing, where AIs like AlphaGo completely shock the world by defeating the best players. We even see it in self-driving cars learning how to navigate tricky traffic, and in huge systems that manage power grids or financial portfolios.
So the bottom line is this. These aren't just abstract theories. They're the actual building blocks for creating intelligent systems that can learn and adapt all on their own. The judge, the rulebook, and the architect, these are the fundamental concepts that are powering a whole new generation of AI. And that really just leaves us with one final big question to think about. If machines can truly master these powerful learning strategies, becoming judges and rule followers and architects, what is the next great unsolved problem that they're going to tackle for us? Thanks so much for joining me.